Okay, we're on. Good. All right, here is a...
Thanksgiving.
Thank you, Jackson, for shouting that out on the recording. I'll be sure and get that in there. That was Jackson Crook, everyone. All right, forces of 150 newtons and 305 newtons act on the hook. The angle between the two forces is 55 degrees. Find the direction angle, and the magnitude of the resultant of these forces. The work you see up here was what we've already done, and we've already established a few things. Now you need to catch a few things. Part of this is having a little bit of physics knowledge, so I'm going to have to impart a few things to you. The first thing, the hook part of things, the hook, and you probably can't see that, but I drew it right here where the green thing is. That's a hook, and you have two forces working on it. One of them is pulling in this direction, the other is pulling in this direction. And in physics, when two forces act on something and they pull away from it, then the resulting vector, in other words, when the hook gets pulled, it's going to get pulled in a direction that looks something like that. So the resulting vector is this green one here, marked W. And what we need to do, when we need to find the direction angle of the magnitude, we need to find the components of W. That's what we need to do. We need to find the components of W. Right? We also need to understand that if we want to find the components of W come from the fact that the two vectors are acting in tandem, so you add the two vectors together. So one of the things you need to get from this problem is that when you have two vectors working on something and it asks for the resultant, it comes from the fact that you're going to add the vectors together. Now, if one of them is working in an opposite direction, it will be a negative vector, so essentially you're subtracting. But just know that you're going to add like that, okay? And we know the angle between the two is this 55 degrees right here. That's marked on the drawing. We also know that we have a red and a blue vector, and the red vector is longer than the blue vector. And so when it talks about forces of 150 newtons and 305 newtons, those are the magnitudes. And the bigger the magnitude, the longer the vector. So hopefully it makes sense that vector U is the 305, and vector V is the 105, just simply because of the drawing and the links. Now, obviously, if someone draws this incorrectly, that could mess us up, but this is drawn correctly for that. Okay, so if both vectors are in standard position, which means that they're situated at the origin, their initial points at the origin, then that means vector U has endpoints right here of 305, 0. So the components for vector U are 305 and 0. Those are the components. Same thing, same idea with vector V, except it is in standard position, but it's not located along the horizontal or the vertical axis. So what we have to do then is we have to drop perpendicular to create a right triangle, and just simply through doing some trigonometry, we find out that the vertical component of this vector, the y part of things, comes from the fact that the sine of 55 degrees is equal to y divided by 150. Now, how did we get that? Well, we know 55 degrees is our angle. We know y is the opposite. 150 is the length of the vector. That's the hypotenuse. And so by trigonometry, our y component is 150 times the sine of 55 degrees. Then, if that's the case, then our x component comes from the cosine. The x component is the horizontal part of things. And so we just simply, through trigonometry, find out our x is 150 times the cosine of 55 degrees. And that's just simply through right triangle trigonometry. And that's another takeaway from this part. Anytime it asks for vertical and horizontal components of a vector, you can always do it if you know the angle and the length of the hypotenuse. You can use right triangle trigonometry. So we know the components of vector V are 150 times the cosine of 55, which that's some number. We'll figure that out in a second. And 150 times the sine of 55 degrees. So we'll figure that out, that part out too. Okay? So now I'm going to stop the recording, and what I'm going to do is I'm going to turn these components into numbers, and then we're going to go back and actually finish this problem. All right, it's recording. We're back now. Yeah. Okay, so this screen looks different than before. That's because I've cleaned it up. And just want to let you know that this part right here, 86.04 and 122.87, that came from the previous slide where we multiplied 150 times the cosine of 26 degrees, sorry. Or 55 degrees, I'm sorry, my mistake, that's 55 degrees. And 122.87 comes from multiplying 150 times the sine of 55 degrees. And then we talk about the fact that vector W is just simply a resultant vector, so it comes from adding vector U and vector V together. So this 391.4 comes from taking 305 and adding 86.04 to it. And this 122.87 comes from taking 0 and 122.87. So we now have the components of vector W. Now we have the components, the rest of it is easy. So the magnitude of W is nothing more than the sum of the squares of the components, square root of that. So it's the square root of 391.4 squared plus 122.87 squared. And we just simply take the square root of that answer right there. So if I am to use my TI calculator, I'm going to have 391.4 squared. That's not going to show. Let's get the right one. So we have 391.4 squared, right? Plus 122.87 squared. And we get that. And then we want to take the square root of our answer. And so our magnitude is 410.232, et cetera, et cetera. So we'll call that 410.23. 410.23. Okay, that's my magnitude. So the magnitude of W, the magnitude of the resultant vector is 410.23. That means that the length of vector W is 410.23. Now, the direction angle, let me group this together a little bit and just slide it up a little bit. The direction angle, if you remember, comes like this. The direction angle theta is always going to be the arctan of the components. All right, the components were 122.87, that's the y component, divided by 391.4, that's the x component. The direction angle will always be the arctan of the y component over the x component in every case. And then we talked about that the other day, that if your angle is in quadrant 1, which this one is because of the way we drew this, it's going to be whatever arctan of that is. If it's in quadrant 4, you're going to add 360 to that number you're going to get, that angle. If it's in quadrant 2 or 3, you will add 180 to it. That's how we'll always find that direction angle. Anyway, bottom line with that, and I'm going to use my calculator. It's not going to show on the screen because I don't know if I'm in the right mode. I need to be in degree mode in the other one. I'll check that later. So arctan, second tan of 122.87 divided by 391.4 gives me 17.4 degrees. So my direction angle is 17.4 degrees. So now we have found both the magnitude and the direction angle of the resultant vector, and we had to do that by figuring out that the resultant vector comes from the sum of vector u and vector v. Vector u is easy because it's just simply a horizontal vector, so its components are whatever the endpoint is, 3050. Vector v we had to find by actually going in and using right triangle trigonometry. And you always find then that the horizontal and the vertical components are going to be nothing more than the sine, the horizontal will be the cosine and the vertical will be the sine of the angle times the magnitude. All right, we are recording again. Hopefully it's picking up my voice. So you have a problem there, a force of 854 pounds needed to push a stall car up the hill inclined at an angle of 16 degrees to the horizontal. Find the weight of the car, ignore friction. I drew a diagram for you right here. So if you're copying this down, you may want to stop the video and draw this on a piece of paper so that you can follow along with me. Okay, the idea behind this is to find the weight of the car. Some people try to solve the problem like this, and this is an incorrect way to do it. In fact, I'll do it in red to show you that it's incorrect. This is an incorrect way to do it. Some people look at the fact that there's 854 pounds needed to push the car up this hill. So 854 is the magnitude of that vector. And then they assume the weight then is the force of gravity pulling downward. So just using simple right triangle trigonometry, they write down that the sine of 16 degrees is equal to the weight, which will be y, over the magnitude, which is the length. So the weight y is simply going to be the magnitude times the sine of 16 degrees. In other words, it's the vertical component of that vector that's pushing the car up. That's actually not correct. So I'm going to put a big X through that, and I'll explain why in just a second. All right, so this is an incorrect way to do this, so I'm going to even erase that right there. I'm also going to pull this vector out of there. The other vector is right as far as that 854 pounds is being needed to push, but in physics, you actually have to look at things like this. When a car is being pushed up when anything is being pushed up an incline, you have a couple of things working on it. One is that, oh, and by the way, on page 434 of the textbook, there's an example of this on page 434 of our textbook. It's example 9. Example 9, page 434. So that may help you to see the triangle I'm about to draw. Right? Well, the triangle then looks like this. You have several things. You have the force of gravity pulling straight down, and that's actually going to be our weight. Force of gravity is our weight. And then you have something called the force against the ramp, which is perpendicular to the ramp. When I mean perpendicular, you'll see it goes at a slant towards the, in other words, it's in the direction that the car is being pulled downward, right? And that actually, and this is the force being pushed up, actually 854, it's this length right here, and this forms a right triangle. Now, if that's the case, then what we have, and oh, and by the way, these are similar angles, so this is 16 degrees also. So really what we have then is a triangle. I'm going to redraw it like this, in which this is our force component right here. That's our angle, and we want to find the weight. Well, the same thing works here then, as far as right triangle trigonometry. Right? If we want to find our weight, then the sine of our angle is equal to our opposite side divided by the weight. So just by algebra, the weight is equal to the opposite side over the sine of 16 degrees. So if let's put a T on that weight right there. So therefore, and I'm using my, you won't see it on the screen there, but if I'm in degree mode, if I do 854 and divide it by the sine of 16 degrees, then I get 3098.2738. So the weight, right, it says find the weight of the car, so the weight is 3,098.3 pounds. The reason I'm using pounds is because I'm dealing with pounds up here. So if I want to...
Probably have to stop.